Hello and welcome to this tutorial for using EuroForMix. This is the basic edition where we'll go through the most common features of the program. So what we will do in this tutorial is first to load the tutorial data. Then we will inspect the data, the evidence and reference profiles. And then we will specify the hypothesis defined and also the model used to calculate the LR, the likelihood ratio, describing the weight of evidence. Afterwards, we will do model validation, which is part of model check whether the model fits the data. And afterwards, we will also go through alternative how to do a model specification searching. Last, we will do deconvolution of unknown contributors. So first of all, EuroForMix is an open source probabilistic genotyping tool for interpreting DNA mixtures using peak height information. It is able to do likelihood ratio calculations, model fit assessment, and also the convolution of unknown contributors. There are also other functionalities, such as database searching, LR sensitivity analysis, non-contributor analysis, relationship testing under HD, and also there is a separate EuroMix module. The model theory is available online as a separate document. This document it describes the model in more mathematical details. There are also other documents such as the source code. It's available on GitHub. There is also a manual how to use the software, and there's a description how the development validation is carried out for each new versions. So on the web page, you can get the manual and validation documents. And also there are links to tutorial videos which are put online on YouTube. In addition, there are datasets available used for either tutorials or publications. There is also possible to find versions of different related software. I will not go into these in this presentation. If you need any help, any technical issues, you can contact me on my email, which is this one. But you can also send it to this email help. But notice that this email is it's checked not very often, so please send it directly to me. Okay, so now we will go through an example for how to use EuroForMix using a tutorial dataset. So we will start off by opening R, and then you copy paste this text that you see here into the R program. When you execute these commands, you will get this window. This is the starting window of EuroForMix. So this automatically loads the tutorial data by using a command line to open the project file. It's also possible to open the project file by load project. So now the selected kit is already selected for you, and also the same for the population frequencies. It's also already selected. But it is possible with your own data to select other kits and also other population frequency files. Also, if you have a new kit, this is also possible to set up. There is also a guide for how to do this on the web page. So now we will look on the profiles which are already imported. So you can do this by checking the profiles you want to view and click the view evidence or view references. This will show the alleles of the profiles. It will also do allele comparison between the evidence and reference profiles. And also it's able to view the evidence profile in a sort of EPG-alike plot, where also the reference profiles can be attached. So first of all, the simple allele viewing and allele comparison it's printed to the R console. So this is how it would look like. You will see how the alleles and heights are arranged for the evidence profile. So this is very useful to do quality control to see if your data has been correctly loaded. Similarly, for reference profiles, you can view the profiles. In addition, it also calculates the random match probabilities for the selected frequencies in the program. It also do the number of allele comparison with the evidence profile, so you can see the match rate between the reference and evidence profiles, and also how many alleles there were missing between these two. What's very useful is to view the visualization of peak heights, like EPG. And here you can see the references P1 and P2. These will be labeled as 1 and 2 under each of the alleles they have. So for instance, let's see here, 15 and 17 allele here is labeled 1 under here because P1 has 15 and 17. And similarly for P2, which has 11 and 14, but these are not shown as a peak height in the evidence. This means they are dropouts. So the nice thing here is that this plot it also shows those alleles not part of the evidence profile. What's also very nice is that you can hover your mouse over the peaks to see more information, the fragment length, the height, and the allele. The line here is the defined analytical threshold. We will come back to how to specify this in the model setup. In addition to the EPG, you will also get a plot looking like this, which is the sum of the peak heights per marker, plotted as a function with the fragment length. This plot it's very useful to have a look on because you can see immediately if you have a degradation in the profile. And this is shown as a ski slope, where you see this black line here. It has a nice ski slope curve. So if this is the case, then you should use the degradation model. We'll come back to that. So before you go on and do the interpretation, you have to go to the settings and see if your settings are correct. Since we loaded a project, these values are already loaded for you. So we don't need to change anything here. So the first thing here is called easy mode. If you put yes, this deactivates the buttons in order to guide the user to do the LR calculations. But for this tutorial, I will not do this since it removes functionalities which we need later on. The analytical threshold is important to define since it's related to dropout probabilities. Also, theta correction is important to specify since this is a way to take into account subpopulation effects. Drop-in model specification is also useful to have a look on, but this is the default value which we use here now. Also, it's possible to define priors for the stutter models, but this is not something you will change. And of course, if you do any changes, you have to remember to do click save here. So now we will do the weight of evidence calculations. We'll go back to the import data panel and select all the profiles. Then you click weight of evidence. First, what we will need to do here is to define the hypothesis under HB and HD. So under HB, we will click P1 and P2 as contributors and select 0 unknowns. Under HD, we will select P2 as a contributor, but then also add an unknown as a contributor, which we will define as unrelated. I'll come back to this. As model option, we will select degradation on and also backward stutter on. This is the most common type of stutter, which we will turn on. We will turn off the forward stutter. So these are reasonable starting model based on our visualization of the data. Also, it's possible to define that an unknown under HD is related to a typed reference. We will not cover this in this video. Then, to calculate the LRs, you have several options, but what we will do here is to use the quantitative LR here. There is also possible to do the qualitative LR as the EuroForMix module, but this is not something we will cover here. So we will first of all do the first one, where you define your model options. We have already defined the options, so we will now calculate LR for that. There's also a possibility to do optimal model search approach, where you are not necessarily sure what model option you want to use. We will cover this later. When you click the button, you will end up with a panel looking like this. Here you have the parameter estimates under HD and parameter estimates under HP. So first, we have that the mix proportion estimates has been labeled as C1 and C2 for each under hypothesis. One way to see which reference this corresponds to profiles defined under hypothesis setup. You can put your mouse over it to get a box showing what contributor this corresponds to. For this hypothesis setup, we have that under HP, C1 is P1, C2 is P2. So it follows the order here. Under HD, we defined P2 as a contributor, but not P1. Then P2 is the first known contributor, which will be put as C1. Then the remaining contributors will be unknowns. So C2 is the unknown under HD, which we see here from the labeling here. Importantly here, what we look for is the likelihood ratio result, which is indicated as original LR values or log 10 values. Since numbers can be very large, it's easier to read off the log 10 values. Also, we have information about the maximum likelihood values from each model. So the log likelihood values, they are not informative by themselves, but they are informative when you compare different models. So is describing how well the model fits the data. So what we use as a model comparison is the adjusted log likelihood. This is what is used on the model comparison, the automatic model selection feature. We will come back to that soon. Also, on this panel here, you are able to do further things, such as model validation, to see how the model fits in peak heights under HB and HD. You can also do deconvolution from here. Also, you can do non-contributor analysis. And also there are some other things such as LR sensitivity. We'll not cover that here. For the model validation, this is useful to do under each hypothesis. You click that and you will get these plots. So the thing you are looking for is whether the points here follows the identity line. So if they are within these envelopes, the model fit is good for the peak heights. Here is an example of a poor model fit where you see the points falling, many points falling outside the red envelope, which indicates a very poor model. In this situation, the person of interest did not explain the observed peak heights, and the LR was also extremely low. But under HD, we can see that the model is fine because we don't restrict on the person of interest anymore. It's also worth to take a look on the parameter estimates, where you can see that these two under each hypothesis had very high discrepancy. We'll now go back to the model selection approach, where you will click, go back to the hypothesis specification, and you will click the optimal quantitative LR. So notice that this approach, it's only a guide, it's not a strict rule. So what you will do here is to specify your search outcome. We will say that the number of contributors is between 2 and 3. We will always select the gradation model, but we are unsure whether any other types of stutter model should be defined. So we select yes and no to both of them. And then when you click OK, you can get a confirmation about the outcome of your search, whether you want to continue. You click yes. So but notice that you typically know beforehand whether you are applying a stutter filter. So if you have a stutter filter, you may don't want to use the stutter model at all. Maybe you want only to tweak the number of contributors. So for this example, we will have a table looking like this, where you see all the model option configurations, where they are turned on or off, and the number of contributors. Importantly, you can see the LR for the person of interest, the mixed proportion of the person of interest, the log likelihood values for each models, and also the adjusted log likelihood is used as a score for model selection. This is the log likelihood value minus the number of parameters in the model. So it's a way to avoid the model to be too complicated. The reason for this penalty is that the log likelihood value will always increase with the added complexity. Last, yeah, and of course the best model is highlighted as a blue one and the one which is selected. as the final model. Last, the number of points falling outside the red envelope will also be indicated as part of this table to get a direct idea of whether the model fits the data or not. Okay, so other useful things is to export the report as a text file. And this report can also include the model comparison table and model validation results. But it relies on that you have done it yourself. Also, when you have done calculations, you can store the results or your session as a project as a separate file. This is useful if you have very time-consuming calculations. Then you can save after the completion, and you can easily load the results again another time. Okay, now let's go to the last part, which is deconvolution. Here, the aim is to estimate unknown contributors to an evidence profile. We want to estimate the genotypes of those. For this example, we will not select any of the reference profiles. So we will specify the following hypothesis that two unknown unrelated individuals are contributors. So we'll do that under the model specification panel. To get to this panel, you will have to click the deconvolution button. If this button is deactivated, this is because the easy mode is turned on the settings. Okay, let's go back to the model option configuration. We will turn on degradation and backward stutter on, with assuming two contributors, since this model was the one fitting best to our data. We'll do the fit, model fit. We will click this button to fit the model. So we end up by having the fitted model under the selected models configuration. We can see that C1 is at 30% mixture proportion and C2 is 70% mixture proportion. So it's a major minor mixture. The model has estimated as that. We can also look on the other parameters here. There is some degradation and a bit of a stutter effect. So notice that the arrangement of which one is C1 and C2 regarded to the values of mixture proportion, they are given in an ordered manner in this version. But notice that for earlier EFM version, these could swap around. It was random which was the minor and the major profile of C1 and C2. So to do the deconvolution, we will click deconvolution. Notice that deconvolution, it gives the posterior genotype probabilities, and these are not the guaranteed true genotype of the contributors. So now let's look on the results. We have a table for each contributor. So now first focus on C2. So we have the top most likely genotype. And then we have the genotype probability. And also we have the ratio to next column, which indicates the probability of the top genotype divided by the second most likely genotype. So it's a way to see how distant that top genotype is regarding to the second one. And this is a very nice measure in order to see if this is a predicted genotype we can rely on. So since we know which are the true contributor, we can also compare that profile and compare with the convolution results. And in this example, where C2 is a major component corresponding to the P1, we can see here that all predicted genotype, they match the true profile. But notice here that quite a lot markers, they have actually quite limited support. Not very small support, but they are very moderate. So there is high uncertainty in these predictions. Okay, next contributor, C1. It's corresponds to the PU2 profile, and this is a minor component with very high uncertainty. Notice that the 99 allele is indicated as a inferred dropout allele, which is not part of the evidence profile. It's unobserved. When we compare the predicted to the true profile, we get quite a few markers which are predicted wrong. And we also see that the ratio to next values, they are also quite low. So this is expected. Last, we can also do a model-fitted p-kite plot, where we can show how the observed p-kite fit with the most likely genotype combination. This is based on deconvolution, where the top joint genotype combination will be highlighted along with the p-kites. So the colors here are the model, and the gray peaks are the observed peaks in evidence. So it's nice to see how these two contributor, they convolve into the evidence profile. Here are the situations where the minor profile component was did not match the true profile. This is something I added in on top of the plot, just to visualize that. So as take-home messages, we have that that it's very important that you inspect the evidence profile and also the reference profiles before doing the modeling. Check the quality, whether there are artifacts and also possible data issues. This is a very common source to errors and strange results. So I can't say it enough. When you come to defining the hypothesis, define these carefully, make sure they are relevant and for the case, and that they assess well. And you should assess how well it explains the data. Also, for the model validation, use it as a diagnostic tool and see if it gives you a reasonable fit to the data. Importantly, interpret LR and deconvolution with caution, since these are both model-based outputs and they depend on your assumptions. And what we see also, treat the deconvolution results with caution, especially if the probabilities are not very high. Thank you for your attention. See you next time.